Hello A2A. So I'm making a video of note 6.6c for anyone who maybe missed or needed a reference of what we were doing. And so I'm just kind of setting up my colors. Now this was kind of a long lesson. So what I would like to do for the video is I'm going to go through things rather quickly, knowing that you can go back over things, plus you have the already filled out notes available to you. So initially we're just kind of looking at the formulas that you will not have to memorize, that will be given to you. So these first two represented a fixed rate. It's growth if you have a plus and a minus. So things like your car or a house, they appreciate or they depreciate pretty much at the same rate. It's not going to change or vary. And then we had the PERT, which is what we use whenever you see the word compounded continuously. But today you're also going to see it with respect to radioactive decay. We will be using this formula. And then the last formula you should be familiar with is the one that has the N in terms of, so here you have a variable rate depending on how many times your money or whatever it is compounded. Monthly, that means N would be 12, quarterly N would be 4, daily N would be 365. And again, you aren't going to have to memorize these, but you do need to know how to apply them. So we're going to start off with an old friend. If $2,500 is placed in a savings account, so that would be our principal, at 5%, that'll be our rate, compounded continuously, that tells me we're going to use PERT. How many years, so we're solving for T, will it take for the money to triple? So A is going to equal 3 times P. So let's make a list of what we know. We know P is 2,500. We know that R is going to equal 0.05. We know that time is what we're trying to solve for. A is 3 times P, which equals 7,500. So 3 times 2,500. And we know which formula we're using. So we can set everything up. We know that 7,500 is going to equal the 2,500 e to the 0.05 times t. First thing we're going to do is divide 2,500 both sides so that this cancels, the zeros cancel, and you get 3 equals e to the 0.05 t. And we are trying to solve for t, so I have to somehow get rid of my e. The inverse of an exponential is a log, and since this is e, we want the natural log, the inverse. What happens is these cancel and this just drops down. So we have ln of 3 equals 0.05 t, so I can divide by 0.05, and then you would go to your handy dandy calculadora, and you would find that that gives you about 21.97, and with years we tend to round to the nearest year. So it will take 22 years for your money to triple in value at that rate. Okay, that is your traditional compounded continuously problem that we've been doing. Now let's look at this concept of radioactive decay. So we have here carbon-14, a very common element, has a half-life of 5,730 years. So if you had 24 grams of carbon-14, you would only have 12 5,730 years later. So not something you're going to sit around and wait for. All right, so we use this fact so that we can actually tell, we can take old fossils and figure out how old they are. We are going to be using the PERT, but now instead of an R, we're going to replace it with a K. It's basically the same thing. All right, so in the process of doing that, we want to know what that K is. We don't know. So we know that the P always represents your original amount, we know that A is going to equal half of P, the half-life, but only when T is 5,730 years. And so from there, we can set up our equation and solve. So this is going to be half of P equals P, e to the k times 5730. So the 1/2 P and the 5730 go hand in hand, and now we start to solve. So I can divide both sides by P, and that goes away. And you're going to find this is a common strategy, so we're going to take the natural log of both sides so that it will cancel with my e. So that cancels, and this just drops down. And to solve it then, we're going to take the natural log of 1/2 divided by 5730, because that's what k is going to equal. And so that is going to give me a value of negative 0.12312. And we're just going to use that as our k. All right. Now, if what you saw in your calculator, you saw like e to the -4, that just means you have to move your decimal 4 places to the left to make your number smaller. Okay. Now, how old is an animal bone that has lost 30% of its carbon-14? So how would we set this up? Well, P we know is your original amount. That's not going to change. We don't know what it is. A, since we lost 30%, that means we still have 70%. So A is going to be 0.7 of your original amount, 70% of the original amount, but only if, again, we're trying to solve for T. So this is when T is a particular number, which is what we're trying to solve for. And K is going to be the amount that we used above, negative 0.12312. All right, so we set it up. We have 0.7P, 70% of the original amount equals the original amount, E to the negative 0.00012T. Now, you might think there's 2 variables here, but again, we divide through by P, so it's gone. And we take the natural log of both sides. You can see there's a certain repetition here, so that this will cancel. And then we have that ln of 0.7 divided by negative 0.00012. That is going to equal T, which in this case is going to tell us how old that bone is. It's going to be 2972.29, so we can round that off to 2,972 years old. Nice. So continuing with the same vein, we have now an artifact originally had 12 grams of carbon-14 present, so that's its original amount. How many grams are left when the artifact is 10,000 years old? So the original amount is 12 grams. The final amount is what we want to know when T is 10,000 years, and because it's carbon-14, we're using the same K. So 3 zeros, 1, 2. So this one's going to be a straight plug and chug to say what it really is. So e to the negative 0.00012 times 10,000. So you just plug that in very carefully on your calculator, and you should get about 3.61 grams. Wow. So there's still something left after 10,000 years. Kind of amazing. All right, now we have iodine. So we're moving on to a different element, which is used to target and kill cells, specifically cancer cells in the thyroid. It has a half-life of 8 days. So what does that mean? Well, if P is the original amount, that means that A is going to equal half of that when t equals 8 days. So it's a very quick half-life. And we do not know what K is here. So that's going to be like what we did with carbon. Let's find our K. So we're going to set it up with half of P, that's my A, equals P, e to the K times 8, because this and this have to go together. The half-life is 8 days. All right, so we start off, divide through by P, they go away. Take the ln of both sides, equals ln e to the k times 8. So we know that these will cancel. So we have ln of 1/2 divided by 8 is going to equal k. And turning that into a decimal, we get negative 0.0866. All right, so we're going to use that k to find out how long it will take, so we're trying to solve for t, a 50-gram sample to decay to 6.5 grams. So now my original amount is 50 grams. The amount after a certain amount of time is 6.25 grams. T is what we're trying to solve for, and K is what we solved for in the last problem. Here we go. All right, so we set it up. We have 6.25 equals 50 e to the negative 0.0866 t. Of course, the first thing we want to do is divide by 50. And I believe, going off of my memory here, I think this was 0.125 equals e to the negative 0.0866 t. So again, remember we natural log both sides so that those cancel. So the natural log of 0.125 divided by negative 0.0866 is going to equal t. So it will take, I think the answer is 24.01, so about 24 days. Now, what I kind of want to point out with this one, because it's kind of cool, you actually didn't even need any trig here, or sorry, any logs. You take half a life every 8 days. So 50 grams in 8 days is going to go down to 25 grams. Then another 8 days, it's going to go down to half of 25, which is 12.5. That's your second decrease. And then the third half-life, you're taking 12.5, and half of that is 6.25. And that leaves you with 24 days. Kind of cool. It all worked out. All right, we're going to introduce two new formulas here. The first one is more chemistry related, where you're relating pH of something, which kind of measures the acidity of an object, and relates it to the concentration of hydrogen ions in moles per liter. That's your H+. And the second one is when you want to compare two earthquakes in order to figure out how much stronger one earthquake was than the other. So let's start off with the chemistry. Not my strong suit, but that's okay. So again, we have this pH scale which measures a substance acidity, and here is a formula we're going to use. Again, you're not going to have to memorize any of these, all right? So they're telling us that orange juice, which I always think is very acidic, has a concentration of 10 to the negative 4 moles. What is the pH? So the pH, if we use our little formula, so what goes here is 10 to the negative 4. Now realize you do not need a calculator for this one because it's a log and I can use my property of logs. This negative 4 can travel down in front. And remember, when you don't see it, that means you have a base of 10. So I have minus a negative 4, which is 4. Log base 10 of 10 is 1. So the pH of orange juice is 4. Very nice. All right, now let's look at toothpaste. Toothpaste has a pH of 9.9. That higher number means it's less acidic. What is the concentration of H+? So now we have 9.9 equals minus negative log, and then here's the H+ that we want to solve for. And you know what? I'm going to squeeze in here base 10, because you're going to want that. So what we have here is unbalanced logs that we want to solve, but you can't do it until you get rid of this negative. You can't have a coefficient. So I'm going to divide both sides by -1. So basically the negative just moves to the other side. That's not that big a deal. And here we have H+. Gave me more room to write my 10. So remember what you do. You write a log as an exponential. So you start at the base, you swing around, pick up your exponent, and set it equal to the argument. So we have that H+ equals 10 to the negative 9.9, and I believe that is moles, or M is what we write, sorry. I don't even know what that means because I'm just not a chemistry person, so I'll just write M. There we go. Okay, so that would be using your pH model. It's basically a log problem where you do have to get rid of the negative because you can't have a coefficient, and you're solving an unbalanced log. All right, our last examples are going to involve when we want to compare earthquakes, which is kind of interesting being a Californian, and we do have quite a few of them. So here's your formula. The ratio that says, what was the, how much greater was one earthquake than another, that's that I over I naught. I'm imagining that stands for the intensity. So you're making a ratio out of the intensity. And then M would be the greater magnitude minus M naught, which is the lesser magnitude. So I don't know if you remember, in 1989, we had a 6.7 Loma Prieta earthquake. I happen to have been living in San Francisco at the time. That was fun. And so what we want to do is find the magnitude of a quake that would be 5 times stronger than the Loma Prieta. So this was 6.7, and 5 times stronger, that's going to represent the ratio of the two magnitudes. So using our little formula up there, we're going to have log of 5, because that's your I divided by I naught, is going to equal M. That's the M we're trying to figure out. We're assuming it's bigger because it's 5 times greater, minus the 6.7 Loma Prieta. Okay, so log 5, remember, is just a number. So I have log 5, I'm going to add 6.7, so I'm isolating the magnitude that we're trying to figure out. And then basically you just go to your calculator, and it turns out that this will be 7.8 is going to be that magnitude, which brings home, you think 5 times greater, that it would be like 30 something, but no. Every decimal point has 10 times greater magnitude in that Richter scale, which is what this is kind of showing. So what if it was a quake that was 12 times stronger? Well, you would do the same thing. So now the I over I naught is going to be 12 equals M minus Loma Prieta, which was 6.7. So log 12 plus 6.7, that's that new magnitude. And that, oh, pooey, sorry, I made a mistake up here because I'm trying to not have this video take too long. This was 7.4. This one is going to be 7.8. Sorry for that mistake. Okay, but look at that. You went from 5 times stronger, 12 times stronger. They're still within that 7 range. That's only a difference of 0.4 if you think about it, but that still represents so much greater of a magnitude. Now, I know you're all too young to remember the 2011 earthquake in Japan. It did result in a massive tsunami, and the magnitude of that quake was 9.0. What we want to now know is how many times stronger was it, so we're trying to figure out this, than the Loma Prieta, and we do know that that was 6.7. Okay, so we have our log I over I naught, the intensity ratio. M is going to be the larger, that was the earthquake in Japan, minus the Loma Prieta. So we have log, again, remember that's base 10, equals, this is now 2.3. So this is what we want to solve. So what we're going to do is, remember, you start at the base, swing around, pick up your exponent, set it equal to the argument. So 10 to the 2.3 equals that difference. And when you actually calculate this out, it's like 199.5. So we're going to round it off to it's about 200 times greater. That's amazing. I mean, think about an actual earthquake. 6.7 was pretty strong. My apartment at that time sustained a lot of damage. I can't even imagine what something 200 times greater would have produced.